Welcome to my presentation in the topic Surrogate-Assisted Investigation of Near-Optimal Solutions for Uncertainty-Aware Energy System Planning. My name is Wanhong. Let's start. So what do you think is the biggest challenge of energy system planning at transmission level? For me, it's very complex. This is also the motivation for 50% presentations yesterday. So when we look at Switzerland, it's a very small country in the European map. But when we look at the power grid of Switzerland, you see it looks so complex with so many nodes and so many transmission lines. So for our Swiss power model CENTIF, which optimizes the generation expansion and operation decisions for Switzerland and its neighboring countries, considering the demand, transmission, and reserve requirements, it uses a detailed power grid for Switzerland and one aggregated node for each neighboring countries as a total of 169 nodes. Even using an 8-hour resolution, it takes the model 4 hours to find the optimal solution. And this is only for an deterministic case. On top of complexity, there is even uncertainty in the energy system modeling. So there are two types of uncertainty. One is called the structural uncertainty. In common practice, we rely on the optimal solution of the model, which is the least cost solution here, so the red point, to provide guidance for energy system planning. But this is, however, being criticized. On one hand, when there's a small change in the input parameter, the optimal solution for the model can be totally different. On the other hand, there are numerous solutions beyond the cost optimal solutions that are only slightly more expensive, but may provide more political preference, which are not modeled in the objective of the model. And on the other hand, there is also the parametric uncertainty, which is also introduced by Francesca already today. So the current method addressing the structural uncertainty is called the modeling to generate alternatives. This method needs to run the optimization problem repeatedly with different objectives to guide the model to find different solutions with different design configurations within a given cost relaxation. So briefly speaking, it is a very computationally expensive method. In the paper that used the method called SPORTS, it runs 150 optimization runs for every trash node. And when we want to integrate also parametric uncertainty into structural uncertainty, we need to repeat this optimization runs for more and more scenarios. And if we want to apply this to our CENTIF method, then the solution for this equation here is over 10 years. It's just a conclusion that the current MJ methods are not applicable on large-scale power grid systems. So we need some more computationally efficient methods that can jointly address structure and parametric uncertainty. So we want to build a surrogate model that can quantify the system performance for different design and parameter space. Imagine if we can have such surrogate model that you give it a specific design and parameter configuration. It can tell you the system cost in only centiseconds. Then when we, Then when we fix the scenario and point and search along the design space, we can find the cheap design configurations for a specific scenario. And when we move along the parameter space, we can see how this design configurations, how its cost is affected by different parameters. This sounds cool, but how we can build such surrogate map of high fidelity with possibly fewer samples? We leverage the method called multi-level informed optimization via decomposed correlation. So the surrogate model learns in an iterative approach. In each iteration, it generates examples of different design and parameter configurations based on the criterion of exploration and exploitation. So exploration is the place that the surrogate model thinks it has not learned very well, and exploitation is where the model thought it's the best design. Then with this given design and parameter configuration, the scientific model runs the operation cost and gives back the cost to the surrogate model. Then the surrogate model needs to build a map with these black points. And this is achieved with the decomposed correlation. So correlation is a method that can interpolate the observed points. And the method can also give you a confidence level of its learning. But this original correlation method suffers from the curse of dimensionality. So decomposed correlation introduces a symmetric layer and a separable layer that can first efficiently capture the structural independence of different dimensions. And then it uses the ordinary correlation, which applies on the overall input domain to capture the cross-dimensional coupling effects. So the introduce of the first two layers heavily ease the burden of the ordinary correlation layer and makes the model more scalable and applicable to high dimension inputs. So this is still an ongoing research, so we implement a simplified case study built on the existing systems and technologies incentive. We investigate the expansion of sex technologies and including renewable and conventional technologies. And as a simplification, the technologies are spatially aggregated, just to notice. So when we mean that we want to implement 10% of battery for all the available nodes that we can implement battery, we install 10% in the available utilization capacity. And for the parameter space, we investigate the net transport capacity from a range of the current level to a reduction of 70%. This is the cross transport capacity between Switzerland and its neighboring countries. And we also investigate a demand rise of up to 20%. So the default value is from the database TYNDP24. And since this is only a simplified case study, the preliminary results I will show is only to showcase the potential of this methodology, but not to provide scientific guidance for policy for energy system planning. So I'm still not responsible for the results. So let's first look at the near-optimal solutions for the default scenario. So we see the solution space for the first threshold is quite narrow. That is because the cheaper solution for Switzerland is to install almost nothing and import everything from other countries. That is also the reason that why the cheaper solutions are not favored. So when we expand the cost relaxation threshold, we see the solution space expanded. And when we look at the near-optimal solutions for the other two scenarios, so when there's a net transport capacity reduction, the system have a strong tendency for relying on the synthetic gas, and followed by a more preference for PV and other conventional technology. When it comes to a rise in the demands, there's a preference for PV, followed by some conventional technologies. But maybe you notice that the solution space for demand rise is much larger than the other two scenarios. That is because the base cost for the demand rise scenario is very, very large compared to the other two. It also shows that it's stupid saying that people use the same cost relaxation threshold for different scenarios. And you may wonder, so for example, for the solutions in the demand scenario, how does it perform under the other two scenarios? So we take 300 solutions from the groups that are within the 10% threshold, and we put them also in the other two scenarios to see how are their performance. So the blue line is the cost for the default scenario for all the three solution spaces, and the yellow line is for the scenario of NTC reduction. I missed something? No, sorry. So to notice the y-axis is the cost for different scenarios, and the y-axis is proportional. So that means the first yellow line is already twice the price as the first blue line. And we see that the solution space for default scenario and the demand scenarios, their cost is quite high in the scenario of NTC reduction. But this is only the solution for three scenarios, and we have a whole parameter space there. So how we can find the solutions that are robust considering the whole parameter space? So we also compute the near-optimal robust solutions and the near-optimal cost stochastic solutions. For the near-optimal robust solutions, since we only have two parameters, so this is the worst case for all design configurations. And to compute the stochastic solutions, we assume an evenly distribution of the uncertainty among the whole range of uncertain parameters, and we calculate the expected cost for every design configuration over the whole parameter space. So we also put these two in the graph, and you can see the cost for robust and stochastic solution spaces are quite low compared to that of demand and default solution spaces. But one interesting thing here is that we can see the solution space from the NTC scenario. It's also very low across all the other scenarios. So, which marks NTC as a crucial uncertain parameter. And so we also would like to have a deep dive into how the NTC levels affect the near-optimal solution space. So when the solution is from an NTC reduction of 35%, we see the cost of the solutions in other scenarios are still not that robust. But when it comes to the 70%, it's quite stable and robust among all scenarios. And so as next steps, we would like to add more granularity on the design and parameter space. So especially, we want to disaggregate the design parameter. And temporarily, we want to include more variability to demand and weather time series. And also, we would like to investigate the impact of fuel and technology cost variability. And also, as the objective of the surrogate map, we can also have import and demand not served to compute multi-objectives. This will also be shown in the presentation of my colleague Francesco in the afternoon. So that's all. Thank you.